Hello everyone, I'm putting this recording together to go over the solutions of the review questions for test 2. I also call this project 2. So project 2 is posted on Canvas already under week 4 and onwards. Please download that and make sure you work through them yourselves and come to this solution to check your answers, or if you're stuck somewhere, then you can just view this and see how it's being worked through. All right. In on test 2, you will be given questions from chapter 13, 14, 15, and 16. All right. So chapter 13 was on chi-squared distribution, the goodness of fit test, and the association test. So the first two questions on this project and also on the test will be on chapter 13. Right? So let's go to the first question. It says population by region. According to the US Census Bureau publication, a relative frequency of the US resident population by region in the year 2000 was as follows. So the first table has 4 different regions of the country. So they divided the regions into Northeast, Midwest, South, and West. And associated with each region is given the what's called the relative frequency values. All right. So these are proportion. What proportion of the population was located in Northeast? What proportion was located in Midwest, and so on. Then the second table says a simple random sample of this year's US residents gave the following frequency distribution. Now, if the project you download says relative frequency, please cancel that out, because over here it says it's the frequency values given to us. 259, 306 cannot be relative frequency values. Relative frequency values have to be between 0 and 1, right? So you should be able to understand that the values in the second table represent frequency and not relative frequency. So let's go on to answering some of the questions here. This is a goodness of fit test that we will be performing. The first question says, identify the population and variable under consideration. The population would be all US residents. We are trying to find the distribution of US residents by region, and the variable that we are studying is the number of residents in each region. All right. Part B says, at the 5% significance level, do the data provide sufficient evidence to conclude that this year's resident population distribution by region has changed from the 2000 distribution? First step is to state the null and alternate hypothesis. Now, we said before that chi-squared goodness of fit test is used for qualitative data. So there won't be a mean or a standard deviation and things like that, all right? It's going to be, you have to state your hypothesis in a full sentence. So the null hypothesis is going to state this year's population. Well, I'm going to add a word here to make it more precise and use a red ink. Null hypothesis says this year's population distribution. All right, that's a very important word, distribution, that was missing here. This year's population distribution is the same as that in 2000. Alternate hypothesis is going to state this year's population distribution differs or has changed from that of 2000. This should be population, right? Population. Okay. After we state our hypothesis, we have to decide on significance level and tail type. So we were asked to perform the test on a 5% significance level. So your alpha is going to be 0.05, and all chi-square tests are right-tailed tests. Chi-square distribution is a right-skewed distribution, therefore the tests will also be right-tailed tests. So keep that in mind. It cannot be a two-tailed test or a left-tailed test. It will always be a right-tailed test. All right, don't make that mistake. Now, the next step is to compute the test statistic. So to compute the test statistic, the best way is to work through a table. That way you will not go wrong. All right, so I'm going to write the formula for chi-squared here so that we can follow along through the table and check against the formula if we are going through the right steps, right? So chi-squared, formula for chi-squared is sigma O minus E whole squared divided by E. All right, so I have it written down somewhere. Hold on. Sigma chi-squared is divided by E. Let me just correct that here. 1 second. The sigma is for the whole thing, so divided by E. All right, so in the first column of the table, we have the 4 regions. And then in the second column, we have the relative frequencies from 2000, from the year 2000. We denote that as P because they represent the proportions. The proportions 0.190. So in the second column, essentially, we are just writing down, noting the values already given to us. There's no calculation, no computations involved in the second column. And it's the same thing for the observed frequency O, which we are just copying from what was given to us in the second table. All right, so do that first. Get all your provided data on the table, because then we are going to calculate in the next column the expected frequency. Now this is a very simple formula. You should all know this. E equals N times P. Not difficult to know it by heart. All right. E equals N times P. So what is N? What is P? P, of course, are all the proportions in the first column. N represents the total observed frequency. That's your N, all right? And you have to sum up all these values here, all right, under observed frequencies. And then, so it's going to be 1500, all right? So when you sum up all your observed frequencies, that's what your N is. N equals 1500. That's what we get after adding all these numbers here. To find the expected frequency, you have to take your N, which is 1500, and multiply by the proportion for Northeast, the proportion for Midwest, N times P. So N times P, right? Let me make this. So you're multiplying this there. All right, so there's multiplication. N times P, and that gives us the values, that gives us the values for expected frequency. So 1500 times 0.190 is 285.0. 1500 times 0.229 is 343.5, and so on. All right. So now that we have the expected frequencies, we have to take the difference. All right. We have to take the difference between the observed frequencies and the expected frequencies. So 259 minus 285 is negative 26. 306 minus 343.5 is negative 37.5. 568 minus 534 is 34, and so on. All right, so in this particular column, we check for the difference between the observed and the expected. And then in the next column, we have to square all these differences, because if you just sum up O minus E, you will end up with 0. All right, it should give you a sum total of 0. Therefore, you have to square it up, square each difference, and then in the next step, you have to divide O minus E squared by the expected frequency values. All right, so what we did here, let me go over that one more time. Minus 26 whole squared is 76. Minus 37.5 whole squared. So again, keep in mind that you are squaring the negative. So your square of difference should all be positive values. That was 1406.25, 1406.25. So that's how you work the O minus E whole squared column. And then in the final column, you're dividing the O minus E whole squared columns by your expected frequencies. Okay, and these are the values, the chi-squared subtotal values you're getting in the last column, which will get summed up. So we get a chi-squared value of 11.209. That's going to be our test statistic. All right, that's going to be our test statistic. So now that we have our test statistic, so the bulk of the work was involved in finding the test statistic, because we had to go step by step and run through this table to get the final answer. All right. In the next part, they ask us to use the critical value approach to perform the hypothesis test and come to a decision. Now, we have to find, for a critical value approach, we have to find the critical value, or the cutoff between the reject and do not reject. But we have to draw our diagram first, right, for the chi-squared distribution. Again, keep in mind it's a right tail test and it's hinged at 0. All right, so your graph should rise from 0. It's a right skewed curve, so please make it slightly right skewed with a long tail to the right. And then the reject region will be on the right hand side, it being a right tail test, and that the area associated with the reject region is 0.05. So we are finding essentially as our critical value a chi-squared of 0.05 with df equals 3. Now how did we come up with df equals 3? The formula for df is the number of categories, that means the number of regions in our data set minus 1. All right, we had 4 regions, right? The number of categories was 4, so it's 4 minus 1 equals 3. Right, so we looked up our table, the chi-squared of 0.05 with df equals 3 is 7.815, right? So 7.815 is our cutoff, and what was our test statistic value was 11.209. So 11.209 is brought over and we check in which region it falls. So 11.209 is greater than 7.815, so it'll fall somewhere on the right hand side of 7.815, perhaps here. So it falls in the reject region, therefore reject null hypothesis. Now let me tell you this, please write this out, okay? We want to see how you came to your decision of reject null hypothesis. Yes, you have to show your diagram and show show it with the reject and do not reject regions and where the cutoff is, as well as where the test statistic falls on the diagram. But in addition, please write out that whatever your test statistic is greater or less than the critical value, and based on that you're taking the decision to reject or do not reject. All right, this is critical. I want to see that line there along with the diagram and the labelings and everything. All right, so we have our decision as reject null hypothesis because the test statistic falls in the reject region, right? What was it? 11.209. And finally, please interpret the test. Even if it doesn't prompt you to, you have to interpret the test. At the 5% significance level, there is enough evidence to conclude. So these are the key words. So I say that over and over again because I see one or two answers not complete as far as interpretation is concerned in the context of the question. So at the 5% significance level, this phrase carries points. There is enough or sufficient evidence. This is important. All right. And then to conclude that the distribution of US resident population by region differs from that of 2000. So everything after conclude, you can just copy verbatim from the question itself. All right, that this year's resident population distribution by region has changed from the 2000 distribution. You can just copy the wording there. All right. Now, if you are writing that there is enough evidence to reject the null hypothesis, that's not correct. That's not a complete interpretation. You have to write whatever the alternate hypothesis states. All right. So you have to write it as that the distribution of US resident population by region has changed from that of 2000 or differs from that of 2000. All right. You just cannot say that it to conclude that we reject the null hypothesis. All right. So make sure your interpretation is complete. Now, the second question on the project is on the chi-squared test of independence or test of association, where we try to find if there is any association between two variables. So this question is on the diabetes in Native Americans. Following is a contingency table showing cross-classification of educational attainment and diabetic state for a sample of 1,273 Native Americans. And this is the data given to us. There are two variables here. Along the rows, we have the educational attainments, and along the columns, we have whether somebody has diabetes or not, the diabetic state. So there are four categories for educational attainment: less than high school grad, some college grad, and of course two states for diabetic, whether they have diabetes or do not have diabetes. So they are trying to find out whether there's any association between a person's educational attainments, educational level versus his versus the person's state of having diabetes or not. All right. I guess the idea is that perhaps people who have a higher level of education are more conscious about their diets and health and are more informed. Therefore, people with a higher educational degree or level are less likely to have diabetes, right? So the question says, at the 1% significance level, do the data provide sufficient evidence to conclude that an association exists between educational level and diabetic state of Native Americans? So it's the population is Native Americans, not everybody in the country, but a certain section of the country based on ethnicity, perhaps. Now, we first have to find the expected frequencies. We are going to use the chi-square distribution for this test. So let's write the formula for the chi-squared distribution here again. It's going to be sigma, all right, chi-squared goes by this formula, chi-squared sub 0. Sigma O minus E whole squared divided by E. Okay. But we first have to find E. The observed values are all these values given to us, all right, in the initial table. And then there I have given you a table over here, but you have to compute the expected values. Now, for association tests, because it involves two variables, the formula for expected frequency is different. It's the row total times the column total divided by n, right? So the n over here is this number 1273. That's the sample size, 1273. And the row totals, right? The row totals are stated here, all right? 251 is the row total for less than HS high school. 414 is the row total. So these are all the row totals, right? And the column totals are in the last row here. These are the column totals. Column total for diabetes and column total for no diabetes, 95 and 1178 respectively. So we have to calculate our E values by taking the row total, multiplying it by the column total, and dividing it by 1273. So to come up with this 18.73 value, this is what was done. Let me write it here. 251, so take the row total where less than HS is, whose expected frequency we want to find. So 251 multiplied by its column total, so that's 95, divided by 1273. Should give you a value 18.73. Likewise, for less than HS and no diabetes, you're going to take the same row total because it's located in the same row for less than HS, 251 times, this time the column is different, so column total is 1178 divided by 1273, right? The denominator value doesn't change. Likewise, for HS grad diabetes, the expected value will be calculated using the row total for HS grad, which is 414, multiplied by column total 95 over 1273. So you're going to go through the entire table cell by cell to compute the expected frequencies, all right, using this formula here, and then complete it, all right? So once we have our expected value, we are going to work through this table. Now, in the first column, I have indicated which row and which column I'm working with. So just note, number the columns. This is column row 1, column 1, row 1, column 2, then row 2, column 1, and so on. All right, and note the observed frequencies first. So 1, 1 at 33, 1, 2 at 218, 2, 1 has 25, 2, 2 has 389. So these values, the observed frequencies, are just copying from what is given to us. Expected frequencies are all the calculated values in this table. So again, just copy your answers that you found for the expected frequencies and jot them down here. And then in the last column, I've skipped some columns here, all right, but you can add some more columns if you wish in order to break it down to more steps. So in the next column, you can have a column for O minus E, and then in the another column you can have O minus E whole squared, and then have this as the last column like we did in the previous question. All right. But I kind of did everything together here, O minus E whole squared divided by E. So essentially I did 33 minus 18.73, I squared it, and then I divided it by 18.73 and came up with all these values for a chi-squared value of 17.518. That's our chi-squared value we obtained after summing up the last column, the values in the last column. Okay, so now that we have our chi-squared test statistic value as 17.518, we can go ahead with the test. So the question says, at the 1% significance level, do the data provide sufficient evidence to conclude that an association exists between educational level and diabetic state of Native Americans? Show all the steps of the hypothesis test below. Again, this time the significance level is 1%, not 5%. So just make sure you're using the correct significance level. First, we state our hypothesis. Again, you have to state your hypothesis as a phrase, as a sentence, really. So the null hypothesis is always going to say there's no association between the two variables. That means they are independent. So here it says educational level and diabetes status among rural Native Americans in New Mexico. Okay, this was even more specific. In New Mexico was the state, which I haven't mentioned here, but that's okay. In New Mexico are independent. That means it is not associated. So if you're using the term associated, then for the null hypothesis you have to say they are not associated. If you're using the term independent, then for the null hypothesis you have to say they are independent. For the alternate hypothesis, it should state educational level and diabetes status among rural Native Americans in NM are not independent if you're using the term independent, but if you're using associated, then it should say they are associated. In step 2, all right, we determine our significance level, and because we have to perform our test at 1%, significance level alpha is 0.01, and we also have to find the DF. Now the formula for the DF is different from the goodness of fit DF, all right, because we again have two variables here. The formula for the DF is rho minus 1 multiplied by, there's a multiplication sign here, all right, so rho minus 1 times column minus 1. So R minus 1 times multiplied by C minus 1. So we had 4 rows, so 4 minus 1, and we had 2 columns, diabetes and no diabetes. Therefore, 2 minus 1, which should have give us 3 times 1, 3. So our DF for this question for association test is going to be 3 for this particular question. So for the critical value, we will have to find the chi-squared of 0.01 with DF equals 3, and that value is 11.345, right? Now the test statistic is 17.518, which we already calculated from our table above. I'm going to just use the critical value approach here. Draw your diagram. Again, it's a right-tailed test, so our reject region will be on the right. The do not reject region will be to the left. You have to show your cutoff or the critical value on the diagram, 11.345. The area associated with the reject region is 0.01, and you have to show where your test statistic falls. 17.518 is greater than 11.345, so it will fall in the reject region. It will fall somewhere to the right of the critical value, and if it falls on the right, it will be in the reject region in this case, right? So for step 4, you have to show all this work. You have to draw your diagram, label it correctly, show where your critical value is, show where your test statistic falls, and then you please include this sentence as well, that test statistic chi-squared of 17.518 is greater than 11.345. I'm going to write that here, is greater than 11.345, which is our critical value, and it falls in the reject region. Therefore, in step 5, we decide to reject the null hypothesis, and for step 6, you have to write the interpretation. At the 1% significance level, there is enough evidence to conclude that there is an association between educational level and diabetes status among rural Native Americans in New Mexico. Again, the key words here in the interpretation on which you will get your grade for this part is at the 1% significance level, there is sufficient evidence or not sufficient evidence, and that you have stated it in context of the question. All right.